let's say we have a problem like this. This is another conservation of mechanical energy problem where we have to account for the work that's being done by friction, which we could also say like this. We have to account for the energy being dissipated by the friction. So here's the problem. We have an 84-gram block positioned against a horizontal spring with spring constant equal to 95 newtons per meter. The spring is compressed 7.3 centimeters. There's a second identical spring in front of the first, right here, and the two springs are spaced a distance d when uncompressed. So if you were to let this stretch back out to 7.3 centimeters, the distance from that uncompressed length to this uncompressed spring is d. The first spring is released, so you let go and this block goes sliding forward across the surface, and it strikes the second spring and then compresses it 4.3 centimeters. Then it stops and it's now at rest. The coefficient of friction between the block and the surface is 0.106. We have to find the distance d between the two springs when uncompressed. Find the distance. Now for any conservation of mechanical energy problem, we say that the initial energies equal the final energies. And then we just add in this extra term when we're dealing with friction. So first let's just write in the initial and final energies. Well, initially this first spring on the left is compressed, so the energy is 1/2 kx squared. Just spring energy, that's all that we have. So let me write that a little bit clearer. We have 1/2, let me write it down here, kx squared as the energy. And then it slides across, and there's some, this spring energy is converted into kinetic energy as it slides. And then it hits the second spring and it compresses this. So at the end, what we have is 1/2 kx squared elastic potential energy, or spring energy. And we don't even have to worry about the kinetic energy between the two springs when the block is sliding forward. Because really in the end, this is the initial and that's the final. And the kinetic energy is just what gets us from this initial elastic energy to this final elastic potential energy. Okay, the first step then is to write down the equation which accounts for friction. And here it is. We say that the initial mechanical energy plus the work done by friction is equal to the final mechanical energy. And here's how to think about this. If we initially have 10 joules of mechanical energy, and then friction does -2 joules, well, the final energy would only be 8 joules. So the work done by friction is always some negative value which subtracts from the initial energy to give a lower final energy. And that's exactly what happens. As the block slides across, the work takes away or dissipates some of the initial energy in the system, making the final less. All right, now, the initial, so now we can just start plugging in. It might help if I were to write out what the work done by friction is. Well, work is always Fd cos theta. And of course, if we're finding the work done by the friction, then we have to plug in the friction force there. So let me make sure my subscripts match up. This is the work done by the kinetic friction. Now, we have to be careful because this d is not the same as this d. So why don't I distinguish by calling this d prime? There. Work by friction is always negative. That's because theta is always 180 for the work done by friction. Here's the reason. As this block moves forward, friction pulls it backward. In fact, friction always pulls in the exact opposite direction as the distance being traveled. So the angle between back, or to the left, and to the right is 180. 180. And that's always true for work done by friction. So the cosine of 180 is -1, and we could simply write that the work done by the kinetic friction is -Fk times d prime. But of course, kinetic friction is mu times the normal force, which is mg here. So that's our equation. Of course, d is the distance over which friction acts on the block. So d prime here, well, we have to look at our picture. When does friction act on our block? it acts as the block slides this 7.3 centimeters, as it slides the D, that distance, and it acts on the block as the block compresses this spring by 4.3 centimeters. So this plus this plus this will equal D prime. Okay. All right, now let's use what we know then to plug into this energy equation. The initial mechanical energy is 1/2 kx squared, like we had written, and maybe we should call this k initial squared. And then we have plus the negative work, so plus negative mu times mg times d prime equals 1/2 kx final squared. Oops. Okay, let's see, kx final squared. Let me write that out. Good. So, we're looking for the distance d, right? Now, we will have 1/2. K is, what is K? We're given 95. Xi, that's how much the first spring is compressed. That's in meters, 0.073. And then we have to add a negative, mu is 0.106, times m. The mass is, so many conversions, 0.084 times 9.81, and I'm still multiplying here, I'm out of space. We also have to multiply by d prime, right? So d prime is 0.073 plus d, it's 7.3 centimeters plus d plus 4.3 plus, so we need the 4.3, which is 0.043. And that's the left side of the equation, which equals 1/2. It's the same spring constant on this for this spring, because they're identical, the problem says. So our spring constant is 95. And the final compression of the second spring, the compression of this second spring here, whoops. So the final compression, the compression of the second spring, right, this spring, is 4.3 centimeters, so 0.043 meters. Okay, and we have to solve for d, which is hidden away right there in this big equation. So I'm going to calculate this out and rewrite it on one line so it's easier to see. So 1/2 times 95 times 0.073 squared, that's point, let me write this in red, separate this out. Actually, let me delete this stuff on work, because we already know that by now. So I'm going to give myself a little more room, erase this here, and now we're ready to go. A little bit more space. So I'm going to rewrite that big long equation, which I've got split onto 3 lines, right here. Okay, 1/2 times 95 times 0.073 squared is 0.2531275, blah, blah, blah. I'm going to store that in my calculator as A. And that value, plus a negative, we have negative 0.106 times 0.084 times 9.81. Enter. So it's a negative 0.0873 dot dot dot. I'm going to store that as B in my calculator. That's being multiplied by 0.073 plus D plus 0.043. So 0.073 plus 0.043 gives us 0.116 plus D, right? And all of this is equal to 0.5 times 95 times 0.043 squared. Did I forget my squared? Squared. Common mistake. Don't forget to square your value of the compression distance, x. Don't forget to square x. And what do I get? 0.0878. So let's add it in. 0878. And why don't I store that as C? So you have to subtract this big thing from both sides. Subtract 0.253 from both sides, right? And then once we subtract 0.253, once you subtract that, we're going to have to divide both sides by this 0.0873, and then divide this by 0.0873. Then we're going to have to subtract 0.116. Okay, you can follow. You guys know how to solve this. I'm going to do it on my calculator and write down my answer here. So when I plug this in, what I get as my final answer for D is 1.776, and we could round that with sig figs to 1.8 meters. Hopefully I've done this correctly. And what I did again is I just took this minus this, then my difference I divided by this, then I subtracted that. And this is what I get, 1.8. So for these problems, the great thing is that you don't have to worry about the kinetic energy that the block has when it's between the two springs, and you can just set the problem up with the initial energy equaling the final energy. And the initial energy is just 1/2 kx squared, the final is 1/2 kx squared. Then you just have to account for the work done by friction, right? Which is negative mu times mg times the full distance over which friction acts. And that's the setup you have. You could have been given this distance, and then, given that distance, you might be able to find, I don't know, you could find x. How far is the second spring compressed? So the same basic equation here can lead us to the solution for any number of different unknowns. All you need is, maybe they give us everything but mass in this equation, and you solve for mass. Or maybe they give you everything but mu, and you have to solve for mu. So this equation is the key. Once you have this equation for this kind of problem, you can solve for anything.